Alright everyone, welcome back. So today we have 2004 C2, where you have some circles intersecting such that any two. So here, for example, this is n equals 3. And you get two intersections per circle, per pair of circles. And you'd like to color it with some number of colors such that every color is used and there's k different colors on each circle. And it's like you want to find which n and k this is possible for. Okay, cool. So like for example, it's clearly possible for one color. I'm curious whether... Okay. So for example, just for n equals 3. Okay, let me say n equals 2 is k equals 1, 2 for vacuous reasons. And in general, n is obviously at most 2n because, you know. Is it possible to do 4 colors? So like, let's say A, B, C, D. Okay, why doesn't this work? Yeah, so you can't do 4 colors. So that's fine. I feel like I am supposed to see something from this, and I'm not. So if a color is used somewhere, like in general, suppose I have a color used. Shout out to N Colors from DJ Mathman. There's only N colors to choose from. Wait, what? Oh, I'm so... read the problem. Jesus. Okay, yeah, we haven't done this. Okay, sorry, I'm stupid. So there's n colors exactly. Forget what I said about k. Sorry, n equals 2. I think k equals 2 is required, whatever. I think n equals 2 is a stupid case, so we're not gonna look at it. Okay, so... Okay, so it's like I have 3 colors and I want to say every color needs to be used. Okay, but I can do like, so this is a coloring that shows that k equals 2 works, right? Like I can... K equals 2 is obviously not okay, but k equals... Or sorry, k equals 1 fails, k equals 2 is... K equals 2 is okay. And can I do it in such a way that every color is used on every circle? I feel like I should be able to, right? It's weird because the circles have 2 intersections. So I feel like the circles is kind of silly. Like, I only care about points in so much as, like, a point is an intersection of 2 circles, and that's it, and there's just 2 each. So really, this is more like I have, done. It's really something like this, where it's like K3, and I want to use every color at least once, and such that every vertex has edge of exactly k different colors. So it's interesting because there's like sort of no reason why this problem should need two edges, right? Like the more natural version of the problem should just be color the edges of Kn, but it's not color the edges of Kn. It's color the edges of Kn where you can use two colors per edge. And I don't know what that's for, but okay. Very cool. In particular, I can always commit to using like the same color for both the edges. So in some sense, if it's possible for like a regular KN, then it's possible for the doubled KN just by repeating the color. Okay, so rather than draw two edges, I'm just going to draw one edge and say that we're like using two colors per edge for like, unknown reasons why. Maybe it makes the problem easier or something. Okay, so I have 4 colors, and I don't know. So I feel like K, N, I don't know, whatever. So A, B, C, we're just gonna try stuff.
You know, who brings art, who brings their vision, and particularly who bring their brain to the table, so that they're aware of what they're doing. And
where's D? Where do I use D? Okay, so I can get K equals 3 without using only single edges. Can I get K equals 2? That should be pretty easy, right? For K equals 2, use like this thing and that thing. So I feel like in general Kn should be decomposed into like...
I don't have a lot of patience for people who feel like they're downloading from the cosmos. You know, just like that's how it came out. Okay, great.
Yeah, I'm so confused. Am I crazy? I checked the box that says instrumental only, right?
Understanding rather than from a place of fear,
I don't understand.
where you're just grateful for any idea that.
Wait, do you not know about Fireboy and Water Girl? Do I want to know? Okay, so here's the plan. I feel like it's mostly possible. Like, it feels like most K equals 1 is always possible, right? Yeah, K equals 1 is always possible. So what we're going to do is we're just going to, like, decompose... Can I decompose Kn into perfect matchings? Is that a thing I can do? Can I decompose doubled Kn into perfect matchings? I feel like the answer is yes, right? What is fire? Oh my god. I'm clowns. So I can... So here's a theorem. If n is odd, then Kn has a decomposition into Hamiltonian cycles. Does that help? NSR is not great, actually. But I just feel like all I have to do is decompose it into a matching, and if I have a matching, then I can just use like one color per matching. I even have doubled edges, so I feel like this really shouldn't be hard. But I don't see it. Yeah. In fact, it doesn't even need to be like. Okay, calm down. So I can definitely decompose Kn as, okay. So, n equals 3, k equals 6 works. Oh, k can be larger than n. I see, okay. No, there's only n colors. Yeah, there's only n colors. So I want to claim so I want to claim I can do k equals n. And I can, does k equals at 2? Yeah, all you do, it's the two things I drew. Alright. So you color all the edges like this, like that. Oh, sorry, I drew the Z the wrong way. Yeah, there you go. So A. So you do all those edges that are in this picture are red, the others are green. Don't you have to use all the colors? Oh, God, frick. Yes, sorry, you're right. Oh, I'm really clowning today. Oh, shit. Okay, never mind. I don't know what I'm doing. I'm really clowning, okay. Oh, that seems rough then. So I have 6, so each guy has 6 edges coming out of it. I need to split them into... Okay, so it's actually the small k which I'm worried about, because I'm like pretty confident I can do large k, like for k equals n or something. The hard part is the maybe for small values of k. You need to use a lot of edges, but each thing should be pretty... So, okay, let's talk about k equals 2. I drew the example for k equals 3, it's not... So for k, it's like, I want to put... First I'm going to put the labels of the colors that I want to use. So maybe I want to do something like this. And I specify the labels first. And then for every pair of vertices, I need to be able to like use that label. Is that right? So this is not good because this is like, so I don't want to do that. Instead, I want to write I hate this. So I don't feel like you can do k equals 2. Yeah, because if I take two subsets of size 2 and I want every pair to intersect, that's not possible. Yeah, so k equals 2 is actually no good. Which is horrible. Mm-hmm. Okay. I hate this. Okay, so I need like what if like n equals 5? I can't even tell what happens for n equals 5. So pairs don't work. Can I get triplets to work? Like ABC, BCD, CDE, DE. This seems like triplets will work. For sets of 3, how big can I get? Because I can't get arbitrarily large things that have... Like, fix k equals 3 and think about n. So, like, what's the largest number of letters I can have such that, like, something is even... every pair intersect? It's starting from 6 that this I'm worried. Right. But I can't totally prove it. Or at least I don't see how to prove it. So the claim is, suppose I have 6 letters. I want to show I can't have subsets of 3 such that all 6 letters are used and every pair intersect. Is that true? Well, what I can do is I can find the... So, you take all the ones that intersect with A, and then all the ones that don't have A. It's like there's some letter that appears, no A. And then these things are pairs. And then these things are triplets. And everything has to intersect each thing here. I don't get it. sucks. Like the one thing you're worried about is like ABC and then DEF, right? Like if I have ABC, I want to show that if I don't have DEF, I can't get DE or F. DE and F. Well, I have 6 choose, there's like 6 choose 3 equals 20 triples that I'm picking from. And really I have at most 10 of them. Because you're almost halved. So if I have at most 10, then there's 30 entries. So everything appears at least 5 times or something like that. So in particular, if there's some entry that appears less than 5 times, like, ah, frick, this sucks. This is not clean at all. Wait, actually, what am I doing? Like, there's 20 things, right? Some of which are in opposite pairs. And all I have to do is make sure that I don't pick 2 diametrically. Like, if I pick ABC, I don't pick DEF. And that's fine or something. Like, let's just say you put them into 10 pairs, you pick one of each, and all I have to do is make sure that every letter is used at least once or something, or twice. So this pure sum sets argument doesn't really extend past why didn't it work for 2? For 2, like the pairing is A, B, C, D, A, C, B, D, and then A, D, B, C. And the claim is that if I circle something goes wrong. What happens is I get all the D's or something. Like they intersect at just D. So I don't even have a It's sort of like a it sort of reminds me a little of Helly's theorem. It's a thing where, like, you know, you have some convex subsets or something, and if any two intersect, then you want there to be like some common intersection to all of them. I hate this. Yeah, it sort of reminds me of that feeling. But I feel like the 4 case is so different from... Like, with 20 things, I think there's, like, no chance, right? That... I guess I can try writing out 20 things and seeing if there's some instruction. I think there's like no chance that I won't be able to pick 10 of them. Wait, no, hang on. The numbers are off. If I have 6 things, what am I doing? What value of n am I trying to do? N equals 6, right? N equals 6. I need 6 choose 2 equals 15. I don't know what's going on anymore. What is going on? You have a K, you have an N, you have... What are the figures? You have Kn, which is a graph on n vertices. You have n choose 2 color sets. You need to pick one per vertex. And you must ensure any 2 chosen ones should intersect. And you must ensure any color should appear at least once. So when k equals 2 and n equals 4, there are 6 color sets. I need to pick one per vertex. I guess I could repeat a color set, but then if I repeat a color set, there isn't a way for me to and any color should appear in some intersection. We won't even worry about this. Is like necessary, but it's not sufficient. Right, and there's n choose 2 intersections. So what the heck is going on here? For n equals 4, I can easily pick 3 color sets such that any pair intersects, and that's fine. For n equals 4, yeah, the low-tech thing is a local thing. It's not global. I hate this. K equals 2 doesn't work because there's no way I can... I feel like it's just everything in the problem feels awkward. Like nothing about, like no condition feels natural to me. Which is unfortunate. I'm just trying to think like even for k equals 3, what's a value of n for which I can prove that it doesn't work or something, and I can't even find that. Like I was trying to think if for n equals 6, can I prove k equals 3 fails? Because for n equals 5, k is so small that any pair of things will intersect. So for k equals 3, I can get a construction for n equals 5. And for that matter, n equals 4. So actually, more strongly, if k is... I think right now, if k is like less than or equal to... If n is strictly if n is at most 2k minus 1, I think I know how to give you a construction. What you do is you take like cyclic things, like for example for n equals 3, k equals 3, n equals 5. What I would do is you take the 5 vertices, right? And let me draw it. So you put like ABC, and you do cyclic shift, BCD, CDE, DEA, and EAB. And now you can just label each edge with the intersection point. So like this is, for example, colored B. You color both the intersections the same color. And this will satisfy, well, by construction, this is exactly the set, but also each thing is used because like symmetry. Actually, let me make sure this is true. Yeah, no, because it's complete graph, right? So if there's a B here, there is a B somewhere else. Hang on. Oh, sorry. This works for n at most 2k minus 1. No, it doesn't. This is for n equals 2k minus 1. And I think if n is equal to 2k minus 2, you can do the same thing and use the pairs. If n is... It might be a little dicier if I have to pick between intersections. So let's say, for example, that like... so I'm still doing k equals 3 cases. So for 4, I think it'll also work. Because I get to use a pair, right? So ABC, BCD, CDA, DAB. So again, I feel like fixed k is better than fixed n as a perspective. I feel like I want to do it like fixed k, do it in terms of n, and then run with it. So here what I do is I write BC instead, because there's circles have 2 intersections, so I get to use up to 2 colors per edge. However, n equals 3, things go bad. Well, n equals 3 is, I think, completely not doable. Maybe? No, n equals 3 is still doable. Jesus, this is so awful. So the color set, there's only one color set to pick. ABC. What is a frame? What did I do there? ABC, ABC, ABC. And then I still am picking the color sets, so, but you can get it to work. AB, BC, CA. So, like, FML, like, I only know how to do it for n equals 2k minus 1. I haven't figured out how to do it for anything else. Well, okay. Let's look at k equals 4. I want to see what happens if, like, for the cases I still know how to do. So k equals 4. N equals 7 is doable. N equals 6 is doable by the construction I outlined. Is that true? Yeah, that makes sure this is true. For... Wait, actually, I'm not sure if the 7-4 one works. Okay, let me do 7,4 properly. So my claim is I can do A, B, C, D, B, C, D, E, C, D, E, F, D, F, G, that's the 7th letter, E, F, G, A, F, G, A, B, G, A, B, C. So the key is that, it's actually a little ambiguous which ones I'm supposed to pick. All I know is this one should be D, so that color is used. If I do C, A, B, and then I cyclically rotate it, then every color gets used. So that's okay if I do that for n equals 7, k equals 4. For n equals 6, I have a hex. Oh, Jesus Christ. I think this is the right shape of constructions, though. For n equals 6, it's A, B, C, D, B, C, D, E, C, D, E, F, D, E, F, A, E, F, A, B, F, A, B, C. So as long as there is a way to do it that is cyclically symmetric, I'm okay, I think. You know, everything else you put like some intersection point. So what I need to do is like, yeah, there's a bunch of intersections, and as long as I make sure that I first make sure that there's a cyclic way to assign it, everything's okay. It helps that I get 2 intersections. Okay, so for example, when I have 5, so it's A, B, C, D, B, C, D, E. God, this is going to be really annoying to write up when I solve it anyways. Right, and my first priority is to make sure there's a cyclic assignment. So, I mean, B, C, D, A will work. And then 4 is fine. So, I think for K, I think for n at most 2k minus 1, I know what I'm doing. I think this cyclic construction is basically the right shape. The problem is this construction starts breaking down when n is equal to 2k, because now you have things that feel like they're disjoint. And hang on, is the construction I gave actually cyclically symmetric? I'm not totally sure it's cyclic. Is that actually cyclic? If it's not, I'm in real trouble. Maybe I don't want to double it like this. But see, here's the thing. This A is forced, right? Like, these two are forced in this construction. And that, I mean, that will be cyclically symmetric. So then I need to make sure... So where do I want to put B and C? I guess it shouldn't really matter. I think I want like... The D there is forced, that's the issue. Maybe I can have multiple Ds though. Maybe it's this. Maybe this is the simplest. Oh, actually it doesn't matter. The point is because I get 2, because I get two edges, when I cyclically rotate if I direct these edges, if I imagine directing them, then everything sort of gets something pointing in both directions, and so everything's fun. Right, like I don't even care about the overlaps, and this will work for, okay. So, B, C, D. Yeah, and so rotate, whatever. And then when n equals k, that's another special case. They're all A, B, C, D. So this case is a little different from the others, but I think A. Well, actually, I think the construction is even the same. It's just a little confusing. Okay, so this should be okay. BC. Yeah, somehow the KN is best thought of as like shoot, no, this is the for k equals n, the construction is a weird case. I hate it. Thank you, CLMT, CRN, RDN, for the follow. Okay, so for n equals k, when it's even, yes, n equals k is different from, I think n equals k looks like it's different from n equals k plus 1 by a lot. But unfortunately, n equals k is also like probably fun. So like A, B, C, D, and you can cyclically rotate this. And then if n equals k, and the parity is odd, I mean, you take the... Well, actually, for n equals k, you can inductively do it by, like, EA, EB, EC, ED, right? So whatever construction you had for 4 things, and then you let this one be EA, EB, EC, ED. So it suffices to do it for a triangle and then generalize. So if k, Jesus Christ. So if k is strictly less than n, 2k minus 1, k equals n, also you can do this separately by induction. Okay, so finally I have the constructions for all k, for all n at most 2k minus 1. And now what I want to do is show that if n is at least 2k, this doesn't work. Jesus, how am I supposed to do that? That's so annoying. So for example, if k equals 3, k equals 3, n equals 2k. So, actually, let me do 2k first. So each color appears in at least like this bound is so dumb. I don't think it's gonna work, but it appears in at least k edges. So in total, how many edges do I get? I get twice 6 choose 2 equals 30 edges. And every color is supposed to appear in at least k edges. That seems... Yeah, I mean, if you can't ignore a color, right, then... I don't know. It's like doubled edges. Oh, that tech is cutting off. Yeah. Well, if n is huge, then like you literally don't have enough time to write all the colors, in the sense that every... Oh, actually, no, that's not true. If n is huge, and like k equals like 3 or something, then you have a bunch of triples, any two of which intersect. Ah, freaking. Why didn't it work for like... Well, for 4 actually there weren't enough edges. Were there? I don't know. Jesus, this is C2. Oh my god. Put E and F here. This is a... No, that doesn't work. That doesn't work. Well, if you can't do it for 4 vertices, you won't be able to do it for more than 4, I think, when k equals 2. I wonder if what I do is I like consider the 2 color sets with like the smallest intersection or something like that. And then do some black magic from there. Yeah. Feels kind of bad, yeah, I agree. I almost don't believe that the task is impossible. Okay, well this is, if this works, this is bad news. I hate life. Alright, so we didn't... Does this work? Because if it does, I'm going to be annoyed. I'm not surprised though. It didn't feel like there was enough to stop it from working. Okay, so for k equals 3, I can do 6 as well. Is that right? Does that work? I think that works, right? I didn't even use the other, yeah. God dang. So what, how big is this answer? Is it like... Well, now I don't know what the answer is anymore. Because for k equals 2, n equals 4 didn't work, but for k equals 3, you can actually still get 6. So I bet you can probably get 7 as well. You kind of do something similar. A, B, C, C, D, E. So rather than skipping E, F, A, yeah, you skip by 2 or something. Oh god. Oh, that sucks. If you skip by 2, is it true that every pair will intersect? It should, right? It's just cyclic shift. No, that's not true. Yeah, no, some of them won't intersect if I do that. I don't know if I can do it for 7. 7 seems like... If I have ABC, CDE... So maybe it's not 2k. Maybe it breaks when I hit k squared. And the construction is horrendous. Oh my god. Oh my god. Please make this problem end. Holy shit. Alright, let's construct 7. Seems like I have a sense of what it should look like. So how do I construct 7? How do I construct 7 in a way that is like cyclic? Maybe I'll specify some of the edges first. And then I get to put one more letter at each of these, right? No, this isn't good. I mean, if I assume with illustrator there's a cycle that is like cyclic, sort of has to do this, right? I don't think I'm losing generality. This problem is really long. I don't know if I'm just being a klutz and like totally missing something. How do you do 7? 5, 7. I wonder, ABD. I need like a gap pattern that isn't All I need is them to intersect. So if I do C, F, and I iterate this cyclically. Oh, no. Ah! Come on. Still doesn't intersect. How did I get that 6 example? It's like... Is there a sense in which that example is just 3 but extended? I don't get it. So I can at least like prove like some really bad bound. Like suppose I have ABC, right? Colors. A, B, C, and then like there's something that intersects this but doesn't use A. Or that, but this is something that intersects at A. Something that intersects somewhere else. Well, every pair intersects really, so... And less than or equal to k squared. I don't even see how that works. The total number of pairs. Yeah, we're still in the C2. I don't even know the answers. I thought that like it might stop working for n equals 2k, but then I found an example for k equals 3 where n equals 6, and now my life is really sad. And like, maybe I should just forget about cyclic symmetry. Do it by hand. Thank you, Red Scratcher, for the follow. Wait, what if I just put A? For some reason I wasn't doing this before, but what if I put an A at like literally every vertex? That way, like things are automatically promised to intersect, and then all I need to do is make sure that some other colors appear, right? Like A. So you put A everywhere, and that way we automatically have the property that any two will intersect. So I never have to worry again about two things not, thing. And then all I have to do now is color the rest of the edges. So, like maybe I put B here. C here. Oh, I've been really bad. Oh crap. Oh crap. Oh, that wasn't. Oh no. This is gonna work, isn't it? E, F, G. Wait, what have I been doing this whole time? Excuse me. Alright, this will work for a lot of things, right? I've been bad. For some reason, I thought that like if a color was used on every vertex, then bad things will happen. But in fact, the exact opposite is true. And if a color is used everywhere, that makes life much easier. And so there should be a large class of constructions where I put like a color at every vertex. What does vertex edges and letters represent? So a vertex corresponds to a circle. There's an edge between there's two edges between every vertex really for the two intersection points. The letters are the colors used at that thing. Okay, so we have been very unintelligent about how we do this. But now, n vertices, there's k minus 1 colors. So all I need is to put k minus 1 edges into the graph. And in fact, edges even double. Such that... Yeah, I've just been... I don't know what I've been doing. Holy crap, I got so misled. But all I need to do is stuff k minus 1 edges. Literally anywhere! Such that every vertex has at least one edge unused. So, degree... So I need you need a graph G such that G has k minus 1 edges and degree of G, the degree of any vertex is less than or equal to hang on, what am I trying to do? No, hang on, now I'm confused again. So I put A literally anywhere. And then I need to pick two colors. I need to pick two colors at each vertex. Oh god, I hate this problem so much. Yeah, okay, let me first do the construction to make sure that I am not off my rocker. So the first move is to put the color A everywhere. And then... Okay, so I have... Okay, here's the construction. So I have 6 colors, right, that I need to use up. B, C, D, D, E, E, F, F, G, G, B. I ran out of colors. We'll just repeat it again or something. Okay, and this will work. So we put the colors B, C, D, F, G, B, or whatever. Shoot. I need to make sure G gets used here. Here, just have a G or something. I mean, it doesn't really matter what you do. Okay, and then make A everything, like put A everywhere else. Holy crap! I'm so stupid. Oh my god. This will work for like very large values of n. I think there isn't any limit on n. I think like you can literally do any n with this method. Like we didn't use 7. We just put A's everywhere. Oh my god. Why did I not do that earlier? Oh my god. Okay. So for k equals 3, like every value of n works, I think. Is that true? Does this work for every value of n? I hate life. Okay, so now suppose we have like general n and k. I'm trying to think like how could this possibly not work for like everything or something, right? So every vertex, imagine it's like A everywhere. Right, so now every pair of things does have an intersection. And then, I don't know, what do you do? I think you just make it work, right? So, I mean, you're promised that k is less than or equal to n. So if I have some value of k, so this, I don't know. This is the dumbest problem I've done all day. So starting from here, right? You do like B, B, C, C, D, D, and so on. And then you might repeat and it's okay. And then like say like k equals 5 or something. D. It's not even constructed, it's just stupid. Like I don't know, I assumed the problem was not trivial. So I avoided constructions where like every color was used somewhere because I don't know. For some reason I had it in my head you could delete the color and dug down. And this is just false. Like if you have a color that's used everywhere, your life is just fine. And everything just works. And it's just like okay, like how did I dispute k equals 2? I don't freaking know. Uh, I'm annoyed. I've been doing this for how long? I'm just like angry now. This freaking problem took so much of my life away. Thank you for the follow from Isaac M23. It's annoying because I have one color that's used everywhere. So consequently, like, I actually have n-1 colors and I really want n. I really don't want to write this problem up. Oh my god. I'm so disappointed. Please don't put this in. Oh man. I mean, this is going in anti-problems. Like, this is just like bad. I can't. It might not be anti. Yeah, okay. Most people might just solve the problem. I don't know what I'm doing. It's supposed to be games. The schedule was always a bit loose. Like, depending on how well the math goes. I thought today might be a day where we solve the problems quickly, and that was exactly what did not happen. Alright, so what's... Wish me luck for my music exam later today. Good luck on your music exam. Okay, so k equals 3. Okay, let me actually do the problem. So for k less than n, we first put a everywhere. So this distinguished color everywhere. Then if k is even, oh, I don't care. I need to make every set have exactly k. So I have n-1 colors. I want to make sure they're all used. So we're gonna trim. We'll have one vertex at the center, okay? This loser here. And then, okay. Now what I do is first I make sure every color gets used at least once. So B, B, C, C, D, D, E, E, and so on. Okay, so let's say Z is the last color. Y, Z, n minus 1 color is not A. Sorry, this is off by a little. Z, Y, Z, X, Y. Okay, so now every color got used at least once. Also, we've used K at least 3 so far. So now all I need to do is randomly throw in colors wherever I want. So I need to increase these things so they are padded to length K. And I can do this just like greedily-ish. So if, for example, K was, I needed K to be so the fact that K is at least n really matters. So this edge used the color B, this edge used the color C. So I need to inflate it such that everything is exactly K. Oh, this is so stupid. Why am I doing this problem? So we for every vertex, we take a directed edge. So example ABC. If I need to inflate to DE, we put D here and E here. So this is D, E. So for this way, I can inflate it to any value of K. And so that satisfies one more condition. And then the last thing I need is to deal with this one special vertex. So I connect it anywhere. And then like write down like B. I don't know. If it's 5, for example, just do A, B, C, D, E. So I'll draw this in a different color. This is a special case. Okay, because I direct these the edges are all really bidirectional. So for any K at least 3, where for this to work, this will work for almost every case. Now I'm trying to figure out what is which cases does it fail for. So it requires K at least 3. Does it require n to be at least K? Does something go wrong if n is exactly equal to K? For example, with 4 for so the circle is n minus 1 things. Okay, so if K equals n, okay, so this works for K strictly less than n, and if K is equal to n, I need to do it separately. Yeah, I think this is fine. So this assumes K is at least 3. For K equals n, I thought I did a construction earlier. K equals n was it's this stupid picture I drew, right? How did this generalize? By induction. So once I had a case for 4, okay, so this is the K equals n case. Alright. Okay, so I've done all K less than at least 3, where K is strictly less than n. I've also done K equals n. So all that remains to do is to check 3, 3 doesn't work, which it doesn't because you can check it, I think. Does it not work? No. 3, 3 works as well, right? Doesn't it? Can I not do like A, B? So for K equals n, you only care about doesn't K equals 3 also work? Does this not work? So K equals n works, right? Okay. Someone earlier told me it didn't. I think I got duped. K equals 3 where n equals 3 also works. So all that remains to do is the special case K equals 2. God, I hate this so much. All right, so for k equals 2, um, so if for k equals 2, if you have AB, suppose like you need a BC without loss of generality, right? You need a different, you need something, but they have to intersect. So now, once you have AB, BC, if you only have B intersections, you die. So there must be AC. And once you have AB, BC, CA, freaking, no, stop. Once you have CA, so then you can't have any more colors. So you get at most 3 colors for k equals 2. Which is probably indeed constructible, right? Sorry, these should be in red. Okay, so this is B, C, A. Okay! This is so stupid. Actually, this argument here may not completely work for... Whatever, it's fine. I think here I should write the letters like... I think if k is exactly n minus 1, this might be off by a little. Oh my god. I almost don't want to write this problem up. Did I get the answer right? Okay, I'm gonna call the answer as when k is at least 3, you can do literally any n. And when k equals 2, you can only do n equals 3 and n equals 2. Oh my lord. I think this will be one of the problems that I don't bother to write up because there's nothing interesting. Did I get the right answer? Did I miss an edge case? Oh, I want to see now. Alright, we're done. So here's the question. Do I want to bother writing this up? Because this is the... And pleasure in grinding and let your students write it up. I feel like I'm worried if like k is at -1. Well, actually it should be okay. Yeah, because I think the green arrows that I'm drawing here are like... Those are all distance, quote-unquote distance 2 arrows. And so if I write A, B, and AC here, these ones are different from this one and this one. And then it's just fine. You know, some of these arrows are bidirectional and... Okay. So, well, let's see what the people want. Switching this. Man, there's so many poll themes. Let's just poke around. We have the StarCraft theme. Yeah. Okay. Well, that's unanimous. I'll put it into the database and write the answer and then... I got baited for so long for this problem. Answer is all nk when k equals 2. K equals 3, any n at least 3. I'm like doing a very brief write-up. It's not a real write-up. I'm just gonna like ignore all the details. So now assume k is less than at least 3. Well, okay. Rephrasing. Kn every vertex has exactly with 2 of n colors, possibly the same color. So every color is used and every vertex has exactly k colors used at it. Okay. The idea is to first assign a color to this special color C to every vertex. we first specify the set of colors at each vertex, then color the edges to make it true to every vertex. So, meaning we always, then we do a annoying construction. See video, details omitted. That's all I'm gonna write. If you type this fast, how did it take an hour to write up USMA 2018-3? Well, I made a lot of mistakes.